probably didn't take you long, right? I'm doing synthetic because I find it easy, and so this one worked out perfectly, right? Which is what I wanted. So interpreting this means that this is my one of my factors, right? X squared minus 5x plus 6. So that was my quotient. My divisor is also part of the, right? It's also part of, it's a factor. These two multiplied together would return me to my dividend, right? What I started with, my big polynomial. Or in other words, my big polynomial can be broken down into these two parts. Agreed? Yeah? Everyone got that as an answer too? All right, now let's take a look. This was my binomial, the divisor that I divided into. This was my quotient. Take a look at the quotient. The quotient itself is a quadratic, right? Can't we factor this one too? And factoring just breaks things into part. That's all that long division does, right? It takes a polynomial and it turns it into a multiplication of two factors. Well, I can do that. Quadratics are easy. I don't need to use any special long division. So for this one, I think it works out nicely, right? Minus 2 minus 3. So my polynomial, instead of rewriting it, I'm just going to say my original polynomial ended up, I broke it into three factors, 1, 2, 3. We say these three factors, okay, and each factor gives you the location of an x-intercept, right? That's what the roots of an equation are. When we replace this with 0 and solve for x, we're finding the x-intercepts, right? We're replacing the y with 0. So if I know, what else do you know about this polynomial? Just the words that we learned since Tuesday, I guess. This was a cubic, this polynomial, p of x instead of f of x, is a polynomial, right? It's got variables, it's got some constant, it's got one constant, some coefficients, it's got powers, and the powers are, the exponents are all whole numbers and they're positive. What type of function is an x to the power 3 function called? Yeah, so this is a cubic function, kind of reviewing the whole unit again. And because the coefficient is positive, right? Again, I gave you two versions of cubic. They're the snaky graphs. They either point up at the end or point down at the end. This is going to be a point up one, right? Okay, so what else? I know it's cubic, so I know it's got the snake shape. I know it points up. Do I know the y-intercept? Close. I think it's -6, right? Wouldn't then y-intercept, if I put zeros in for all the x's, these guys would all disappear and I'd be left with -6. Okay, so the y-intercept is -6. What are the x-intercepts? Well, we just solved them. We used long division to solve them. Long division and factoring. So the x-intercepts are 1, 2, and 3, right? Okay, do you have enough? Do we have enough info to make a real quick sketch? Not even with graph paper, I'm just going to do a real quick sketch. Okay, really raw, I'm just going to do this. Guess I have to 1, 2, 3, 4, 5, 6. Okay, y-intercept, -6. X-intercepts, 1, 2, 3. And now you just have to kind of connect the dots. I know it's a snake graph, positive snake graph kind of, and I know it can only cut through the x-axis these many times, right? If it's got to end up, I'm going to kind of start backwards. It's got to look something like this, right? And that's it. It's finished with the x-axis. So it must look like that, more or less. Agreed? Now, I don't know how high these guys go. We can figure that out later. But that's it. That's really what this unit's all about. That's kind of the whole unit in a nutshell. Now, to be able to do that efficiently, we have to know how to long divide. Yes, check. We know how to do that. We know how to do that if we're given the a value. On Monday, I'm going to tell you how you can figure out a good a value. And you know what else we have to be able to do? When you get to this part, you have to be able to factor, right? Which you learned. But we're going to I'm going to do a quick review. That's why we have a little review in the both packages. I'm just going to draw your attention to your examples workbook. It says factoring polynomials, and it says, because it's all about factoring, right? We have to factor to get the binomials that contain the x-intercepts. It says in previous courses you learned 4 main types of factoring, or binomials and trinomials. So these are how we've divided them up. Just common factoring, GCF, and finding a GCF, right? Greatest common factor. Because this isn't a trinomial, right? You spent lots of time on trinomials. Then these guys, these difference of squares, they pop up every so often. So you have to refresh yourself on those. These are probably these are your classic trinomials, right? A squared, an x squared, an x, and then a constant. These are easy to factor. You should be able to do these types by just looking at them. These are the more complex, right, when A is not 1. These require a little bit more skill and practice. And the reason we're doing that is because it helps us to find our x-intercepts. It helps us to graph. So let's just quickly, is everyone familiar with these guys? You've seen these types. Now the other thing about this, like one of the reasons we chose this book, like I say, is I am going to add a couple more assignments. They're quite small, like none of these assignments seem very big. In this book, when you flip the page after your remainder theorem stuff, it has a review of factoring, which is, when I go through these examples in class, if you're kind of rusty, look through this book. It gives you lots of other examples, and it gives you some more worked examples if you need some practice on how to factor again. All right. This is not a trinomial. There's only 2 terms to it, so there's not much I can do except look for a greatest common factor, right? So what's the greatest number, the greatest coefficient, the greatest terms that these 2 terms have in common? 3xy, right? When I factor out 3xy from this term, I'm left with 1, right? Plus 4x cubed y to the 6. And that's it. That's all you can do. Let's just double check to make sure we did it properly. 3xy times 1 is 3xy. And then this times this would give me my 12x to the power 4, y to the power 7. So there's lots of review in here too, right? You have to know your laws of exponents. Now here I have 3 pieces, so it looks like a trinomial, but it's not, because the variables don't have that pattern, right? The square, the x, and the constant. So again, I got to look for the largest number that divides evenly into all of them, which would be 5. And how many m's do they have all in common? They all have m squared in common, and they all have an n, and that's it, right? So again, I have a 1 plus 5n minus 9 m squared n to the power 4. Yeah? Now, pulling out a GCF is crucial. Anytime there's a greatest common factor, pull it out, because it reduces the numbers, or it reduces the size of the numbers you have to work with, right? Anytime you can reduce using a greatest common factor, do so. Difference of squares occur a lot. Do you remember your difference of squares have a 0 middle coefficient, right? Like this is in reality, it started out as x squared plus 0x minus 100, right? But to rewrite it, we would never have that 0x. So the only way to get a 0 middle coefficient is if your second terms cancel each other out in the middle. Well, how would they cancel each other out if one was a minus and one was a plus, right? Because if to check this answer, that's how we get the 0 in the middle. To check the answer, I'd get x squared, I get my positive 10x, my minus 10x, and my negative 100, right? These guys cancel each other out, leave me with 0x, which I would just record as x squared minus 100. So difference of squares are easy to pick out, like they're two terms connected by a minus sign, a difference, a subtract sign, and they're both perfect square numbers, like the x squared and the 100. Okay? They're really nice to factor. What factoring does, once again, it takes just a regular polynomial that's connected by an add or a subtract, and it turns into a multiplication statement. Those are great because only with multiplication statements can we cancel things, right? If I have to embed this in another equation or add it to another term, through canceling or through multiplication I can cancel. Okay, is this a difference of squares?
Yes.
Okay. So the square root of 64x squared, 8x, right? So 8x's go here. The square root of 25y squared is 5y, plus minus. It doesn't matter which bracket the plus or the minus go in, as long as one bracket has a plus and one has a minus. 4 minus 49m squared. Is that a difference of squares? Yep. Okay, set my brackets up. Square root of 4 is 2. Square root of 49m squared would be 7m. Plus minus. Right? Now the reason is after your long division, after you do your first long division, you'll have a binomial, the one you divide it into, and then you'll have a trinomial, or it could be a difference of squares you're left with, right? You have to be able to factor that last piece. Okay, simple trinomials. I hope everyone's fine with these guys at this stage. Yeah? So if the a value is just 1, you should be able to just inspect it and figure out what your values are, right? I'm looking for numbers that multiply out to 12 but add up to 7. 4 and 3, right? 3 and 4, 4 and 3. Anytime your constant is a negative, you know your signs, one sign has to be a positive and one has to be a negative. Okay? Because the only way you get a negative product is a plus or minus. Okay, so I have x's here. Numbers that multiply out to be 45, add up to be 4, it's got to be 9 and 5, right? And the 9 has to be the positive. Because a positive 9 subtract 5 gives you positive 4. Okay, here we're using v's instead of x's. Again, one of my brackets is plus, one's minus because of the negative 63. What two numbers multiply out to be 63 but have a difference of 2? 9 and 7. Which goes where?
9, negative.
Negative 9, positive 7, right? Because that's the only way to get the negative 2. Okay, the more complex trinomials, again, I think they go through some examples and they go through some, I think, how to factor these guys, and probably lots of students learn this in different methods. There's the inspection method, and I think they're doing it on page 65. They break it down. How did you guys learn how to factor these? You find 5 times 4 is 20, factors of 20.
Whatever, like
gives you.
Add up, but multiply to 20.
Okay. I don't know why we left, so I think we'll have to move this up a bit. I'm going to show you how I do mine. I'll do the similar system, and I'll just show you. I'm just going to move up here just to give myself more room. So I do the same thing, like that's a foolproof method, right? This one actually is not that hard because 5 is a prime number, right? So you know it only has 5 and 1, and 4, there's not many factors of 4. Same with this one. They should all be fairly easy, but sometimes you do get larger, like if this was an 8, and that might have been like, I don't know, like 24. When you have lots of partner factors, it's kind of hard to single in, but I'll show you a foolproof way. So as Eduardo said, I have to like we were actually doing the same thing up here, but because the coefficient was 1, 12 times 1, you're just looking for factors of 12, right? But an a value other than 1 changes things. So I look for factors of 5 times 4, positive 20, okay? And everything's positive here, so it's kind of nice. I'll have to do a negative one as well. So what I do is I list, if you're just beginning or you're really rusty, I list my factors of 20 in pairs. So I have 1 and 20, 2 and 10, 4 and 5, and I believe that's it, right? Okay. And I'm sure you already know what the answer is, but because everything's positive, I don't have to worry. Everything is, all numbers are positive because these two positive numbers multiply out to give me 20, but only one perfect partnership adds up to give me 9. And the other thing I'll tell you is I always put my small member on the left-hand column. My large member of the group is on the right-hand column, and I'll do that for a reason later on. Okay, this plus this gives me 21, this gives me 12. There's only one combination that'll ever work, right? So here's your 4 and your 5 give you 9. That means that I take my 5x squared plus 9x plus 4. The 5x squared and the 4 stay. The 9, I break it apart into a 5x and a 4x, right? Now notice I switched the order. I didn't put 4 first and 5, because basically what you're doing is you're taking a trinomial and you're making it bigger. You're making things worse actually at the beginning. You're exploding a trinomial into a polynomial with 4 terms. And the reason you're doing that is to be able to, does anyone know what the word I'm looking for? You're going to factor by grouping, okay? And the only way I can group things is if I have even partners, right? So these two guys are going to group together, and these two guys group together. Then I look for GCFs of both, GCF, GCF. Okay, greatest common factor between these two guys is 5x. That leaves me with x plus 1. The GCF with these guys is only a 4. Whatever sign's here just gets repeated. As soon as I do that, by the way, these guys always have to match. If they don't match, you've done something wrong. Okay, so now the GCF between these two pieces is x plus 1. And I'm left with 5x plus 4. And you're factored now. Okay, I want to do this one too. I'll do this one too because it has a negative sign at the end. I can do this one as well. So this one would require factors of negative 12. Agreed? Because 6 times negative 2 is negative 12. Okay, negatives are a little harder to work with as always. I list my factors of 12 in pairs again, the little partner on the left, the big partner on the right. So I have 1 and 12, 2 and 6, 3 and 4, and that's it, right? Now I inspect my original statement. When these guys are combined, I end up with a positive number, right? That tells me that the positive member of the partnership has to be the positive term and the small member has to be the negative. Because that way I'll always get a positive answer, right? Negative 1 plus 12, positive 11. Negative 2 plus 6 is positive 4. Negative 3 plus 4 is positive 1. Okay, that's what I'm looking for. So those are my two numbers that I'm going to use to break things apart in. Okay, so my 6x squared stays the same and my negative 2 stays the same. I just have to break this 1x apart into individual components. Negative 3x, positive 4. I think the 3 partners nice with the 6 and the 4 with the 2. So negative 3x, positive 4x. Right? Again, making things bigger at the beginning. So I just converted my 1x into a negative 3 plus 4. Okay, so now I can group these two, and I get the biggest thing they share would be a 3x. That leaves me with 2x minus 1. They only share a 2. 2x minus 1. Again, I have GCFs of 2x minus 1. And I have a 3x plus 2. And that's factored. Okay. Now, if you don't need this process, you might be able to do it quicker, right? I don't know. You could try and start off just by kind of inspection. You could say, well, by the way, 3, the only way to get a 3 is 3 and 1, because it's prime, right? The only way to get a positive 3 is the signs have to match, right? They both have to be positives, they both have to be negatives. In this, here everything was positive, here it's not, so these guys both have to be negative, right? Okay, I'm almost done. Now, the only thing I guess you have to think about is this a 4x and an x? Right? Or is it a 2x and a 2x? That's about it. That's all you have to figure out. Or is it x and 4x? So let's see. 4x squared minus 4 minus 3. Well, I kind of just got it. Just by kind of fluke in a way. But you get better and better at this, right? So 4x squared minus 4 minus 3 gives me my 7. Negative 3 times negative 1 is 3. Right? The more you know about numbers, the quicker you can become at this, right? So what we're doing all the time is we're factoring in order to find our x-intercepts, because these will be, it says now solve the following equations. Well, this is already in factored form. The only way I'm going to get a 0 answer is if x equals negative 3 or x equals 1, right? Here, well, we have to factor first, right? Which is why factoring is so important. Again, these are really easy because 2 and 3 are both prime numbers. So I just have to figure out if the 3 goes here or here. I get a 3 and a 1, or let's see, 2x squared. No, I think it was the other way, wasn't it? Plus minus 2. Nope, it's got to be this way. Just kind of doing mental gymnastics. Okay, so I get 2x squared plus 6 minus 1. Right? 2x times x is 2x squared. Positive 6 minus 1 gives me positive 5x. Negative 1 times 3 equals negative 3. So 2x minus 1 times x plus 3 is 0. That must mean that x equals 1/2 or x equals negative 3, which would be the x-intercepts of this quadratic function. Okay, so lots of talk today. This was all review, and like I say, you can, I'll write this in the book, you can review factoring on pages, I think it starts with way back, 62, 63, 64, 65, 66. Okay, so also if you want, you can do 62 to 68 has lots of factoring review. And then I'll also assign for you, in addition to those, do numbers 1 through 20 on page 70 to 71. Now, if you don't need any review on factoring, if you're solid on factoring, that's great. Then you don't have to do any review. But just throwing it out there that there is some extra work in there.
But all that stuff is all fine.
This stuff's all factoring, yeah. It says, well, actually, some of them have been factored for you. It says solve each equation, identify all roots. So those are just solve for x, right? So these are already factored for you. You do have to do some factoring. Eduardo, down here you'd factor, you do some factoring here. Here it says find the zeros, which is another name for x-intercepts, right? Zeros is another name for x-intercepts. So definitely you have to factor some of them, but some of them have already, looks like they've been factored for you. So you're just solving for x, sorry. Zeros and x-intercepts are the same thing. Okay, we still have a few minutes left in class, so stick around, and if you have any questions for me.
Yesterday when we were doing it,
Yeah.
we were doing, my group was for synthetic division of
Make synthetic division fractions?
yeah,
Grab a
like,
seat.
I mean, I think that yesterday when you showed me like the multiplier divide, like whatever the coefficient is. So yesterday you showed me that we just divide by 3 and then we can start the process when we do the synthetic multiplication. And today we're doing the remainder theorem. I was gonna divide by 2 on my coefficient and this one, but instead you said that we can just zero out on one side and the other one.
Yeah, if you're just looking for the A value here,
Why? I guess my question is like, why is it different?
yeah, so let's see.
Yeah, because I did this one we divided by 3. I mean, I guess this one is because we're actually dividing it, and this we're just finding the value of beta, plug in, substitute.
Different process, I'm just trying to tell you. So.
Because I understand how we can,
Yeah. Right?
and I'm like wondering why
You're
this
okay
is
with
different.
this, it's just,
Yeah, like I'm like what equals 0 and then finding the new A and then plugging it in, like that's fine. I'm just wondering, how do I know when to just do that and when I can do that?
I know that really screwed you up. Right? Ay, ay, ay. So let's just say that the A value is 3 here.
Yeah.
So there's no conflict here. A is a third, Y is a third, right? Let's forget this for a second. Let's not do that. Let's not show it.
Let's just do it by 0. Yeah.
So same thing. So Y is a third, Y is a third. That is a third. Agree?
And then we can just plug back in without having to worry about fractions, right?
So if I wanted to find the value of this polynomial, right, I would just put 1/3 into here because I want the value of the polynomial. But when we're doing a division statement, dividing is always going to make everything smaller, right? So if it says divide, they actually want you to divide the A value into here. Right? This remainder theorem, like it's not really a conflict, they're just two entirely different processes. This is just telling you find the remainder when the given polynomial would be divided by each polynomial. We're not actually doing the division, we're actually finding the value of the polynomial.
It's kind of like doing the discriminant and not using graphical.
Yeah. And
Right.
so here it's actually saying do your division. So showing that division by 3, which way were you doing it again? Were you doing it like they did it?
The synthetic?
Yeah.
I was doing it both. It was like, I remember Mr. Beecham taught me this way. I would
No, but he didn't ever show you with the 3x plus 2 though.
No.
Because you never had an A value other than 1.
No.
So here in the book, I think they did something wrong here actually. Okay. Let's pretend that I didn't, like just forget that 3 there that I had there. I'm going to erase everything.
Just a quick question before you do erase it. If we do it this way, we end up with the same values as if we do it the other way?
Yeah.
Okay.
This is the way, I showed it this way because they're asking you to take your, take everything, take your whole thing and divide it by 9y cubed plus 2y plus 1. Dividing is completely different than find the value of it. Find the value of p of x when x equals 1/3, we'll say. Okay? So I'm just going to, that 1/3 is whatever value zeroes out your
Right.
right?
Yeah.
So you're going to put your you're going to put your 1/3 in, right? Plus 2 times 1/3 plus 1. So that's going to be 9 times 127 plus 2/3 plus 1. So I have 1/3 plus 2/3 plus 1, and that's going to be 2, I guess. Okay? So that's just finding. That's
remainder.
finding the value, right? That's finding the remainder. Your remainder theorem. This is using the remainder theorem.
And again, we just use remainder theorem to determine whether we can or can't graph something.
So this is not one I would be graphing because it's got a remainder and it wouldn't, I wouldn't solve with this factor, it wouldn't factor, and I couldn't go any further than just finding remainder, and then that's what I've done, so I can't, it's not really factorable. Now here, we're actually dividing into, right, we're doing our 3y minus 1 dividing into 9y squared plus 2y plus 1. So what you do, you said, oh no, I want to do synthetic division, okay? Well, it's really complicated to do synthetic division. So what synthetic division does, it breaks this division into rows. Yeah, so first I'm going to divide by, because I can't really do synthetic with the coefficient. That's the problem. So I'm going to transform this into two parts. I'm going to pull my 3 right out of here, and that's how I get my y minus a third. Okay?
Oh, because it
That's
multiplied
what
back in.
happens.
Okay.
So it's not really the same thing as taking this,
And dividing by.
and so it's not the same as taking this and equaling 0. It's not really the same as finding the 0 value. I'm actually factoring my 3 out. Okay? So first we do our synthetic with this, right? So I take my 1/3 and I do my division of my 1/3. So that's going to be my 9,
Would it be
0, 2, and 1.
negative a third or a third? After you
Oh,
start.
a third, thank you. Okay? So I'm going to drop my 9 down by, and that's going to be 3, 1, 2. Okay? So here's my remainder 2. This is what I was left with. Okay? 9y squared plus 3y plus 3, right?
The remainder.
Remainder 2, and then I had, this was my binomial factor, right? So this times this plus 2. However, remember I was supposed to divide by 3y minus 1, and I only divided it by y minus 3. I haven't divided this 3 into anything yet, right? Okay, so I took this and I divided this part into that, but I didn't divide the 3 into it yet. So now I'm going to take care of the 3.
Oh.
That's how that becomes 3y squared plus y plus 1. Got it?
Okay.
You're breaking your division into 2 parts. And then I have my plus 2, okay? Which was over the remainder, I guess, which was y minus a third. Sorry, Shelley.
Sorry.
So if I want to put it into proper form, and then I would still have my, so p divided by y minus a third equals this plus this over this, right? This divided by this equals this plus this over, that's how you just square your remainder. Now, if I could multiply everything, if I multiply this again, and I could just say, okay, now p equals, I can also say p equals this times this plus 2 over y minus a third. Right? I wrote it in that form. I would be multiplying this by this and this by this, which would cancel out. So that's what it would be left with. But that's what the division does. That's where that 3 piece in.
Okay.
You divide this piece first, and then you divide by the 3 at the end.
The coefficient afterwards. Okay. Okay.
That.
Alright. This is mine.
Is that yours?